professor near Bar-Gill. He completed his undergraduate and master's studies in physics and electrical engineering at the Technion. Later on, he completed his doctorate at Weizmann Institute in 2009, studying ultra-cold atoms under the guidance of Professor Nir Davidson and Professor Gershon Koriziki. He received the Otto Schwarz Fellowship for Excellence in Research and the Feinberg Dean Prize for PhD students. Bar-Gill then spent the next 3 years as a postdoctoral fellow at Harvard, working in the group of Professor Ronald Walsworth. His main contributions are in understanding nitrogen vacancy spin physics and to extending the nitrogen vacancy time to nearly 1 second. He received several awards, including the Minerva Arches Award, the Saipar Azrieli Global Scholar Fellowship, and the ERC Starting Grant at the Wolf Foundation Creel Prize. Nir joined the Hebrew University in 2013 as a joint appointment between the Department of Applied Physics and the Rakach Institute of Physics. His research aims to create platform for both fundamental studies in quantum science and interdisciplinary application. Specifically, he is researching the nitrogen vacancy color centers in diamond, which can serve as a building block for quantum information processing and for quantum sensing, for quantum simulation of many body physics and quantum thermodynamics. Today is going to talk about how we can harness diamond for quantum technologies. Quantum information and quantum technologies are becoming a major field in current scientific research with clear and significant potential for impact on our society. As an example, Google has declared last week, actually it wasn't last week, it was a few months ago, I'm reading, so sorry about that they have demonstrated quantum supremacy. That's an exponential speed up in calculation performed by their quantum computer compared to the fastest supercomputer in the world. He will discuss these topics and present them in the context of his group's research, which focuses on atomic defects in diamonds as a platform for quantum science and technology. Specifically, he will describe how our system can be used as a qubit, the building block of quantum computers, and how the diamond quantum technology could contribute to medical diagnostics in the form of enhanced MRI. Nir, you can take it from here.
Excellent. Thank you very much, Shmulik and Miriam. And it's a pleasure to be part of this very nice program of webinars. I'll be talking in the next half hour or so about, as Shmulik said, about my research into quantum technologies using diamond. And I'd be very happy if if any questions while I present, I'd be very happy to stop and try to clarify and answer them as best as I can. So please feel free to interrupt and send questions. So we're talking about quantum, and we're talking about diamond, and how these two things kind of come together. And that's what I try to explain in the presentation. And I'll try to do this in the context of the quantum revolution, or basically what we're in the middle of these days, how quantum science is starting to transition from something that's very fundamental and not very useful into potentially an actual revolution in our day-to-day lives. I'll give two examples that are relevant to my research. One of them is in the context of quantum computing, trying to use the power of quantum in order to get faster computers, to be able to build faster computers, and I'll try to explain that a little bit. And another aspect of this quantum revolution is trying to do something other than computing using quantum resources, and I'll give an example in the context of sensing, or specifically medical diagnostics, such as MRI. So these are the two main aspects, two topics that I'd like to touch upon in the under the framework of this of the quantum revolution we're living through. So I'll start with computing, and before I start talking about quantum computing, let me just go back a little bit and talk about regular computing. And this is my view of regular digital computing. We all love it. We all use it all the time. Even our cats love them. And we all know, of course, I mean, I don't have to convince you that digital computing is a real revolution, and it's really useful. I mean, we all have these computers in our pockets, and we use them all the time. And it's pretty clear what these things allow us to do that we just couldn't do before. So if we think about how this whole thing started, and we really go back to the 40s, to the Second World War, we can really trace the beginning of this era of digital computing with a specific need. So the specific need that kind of propelled this field forward was the need to be able to do calculations fast. And the fast calculations that were needed at the time were to be able to break codes, to be able to break secret codes that were used in the war. And the very well-known example of that is the need to break the Nazi Enigma code in order for the Allies to be able to gain some advantage in this war. And to do that, the British recruited one of the brightest minds that we've ever had, Alan Turing, shown here, is a very smart mathematician, and also in some sense the father of modern digital computing. And he was able to build a computer. Basically, this is a picture. This is, I think, a model, but it's an exact replica of the computer built to break the Enigma code, the Nazi Enigma code. It's called the Bomba, and it worked. So the capabilities of this new machine were instrumental in giving the Allies an advantage, allowing them to break these secret codes that the Nazis were using, and to really make, get a significant advantage in the war. So this is an example. This is history, but it's also an example of how computing started. Regular digital classical computing started from a need, from a security need or defense need in the Second World War. And I can imagine that at the time, Alan Turing was really focused on being able to build a machine that would be able to do calculations fast enough in order to break these codes. But I can imagine that he didn't really think about what implications that would have in the relatively far future, maybe 50, 60, 70 years in the future, where his basic idea of a digital computer would allow us to, I don't know, play games and be on Facebook and send pictures on Instagram. So he probably didn't think about that, but things evolve amazingly fast using these technologies. So this idea of being able to use the digital basis in order to do fast computations essentially relies on storing all the information and making all these computations on basic units of information that we call bits. And these bits are essentially, each bit simply encodes either a 0 or a 1. So instead of writing using large alphabets and different letters, we can store all the information just using many bits that are each one of them either a 0 or a 1. And if we write a long enough string of these zeros and ones, we can encode all the information that's in the world, and also compute it, use computations on it. So this is the basic idea and the basic unit of information that lies at the heart of regular classical digital computing. And maybe just to mention an interesting connection to the early days of digital computing, even today, we use various types of encryptions. We use different types of codes to hide our information. And you all use them. I mean, if you want to go online, to shop online, or to go to your online bank website and do some transactions, you want it to be secure and you want it to be encrypted. So we all use encryption all the time. And actually, almost all of us use a very specific type of encryption that's called RSA. RSA stands for it's an acronym for the names of the inventors of this code. The S here is Adi Shamir from Weizmann here in Israel. And the reason why everybody uses this type of encryption is because it's unbreakable. Nobody knows how to break this code in a reasonable amount of time. So of course, the simplest approach is to just try all the different options, but that would take a very, very long time. And we can actually use a very long code to ensure that if we just try all the different options, it's going to take, you know, the age of the universe to be able to crack it. So it's completely impractical to be able to try and even crack this code, and that's why everybody uses it. So even today, this idea of using codes to hide our information is very relevant in the civilian scenario, as I mentioned, and of course also in defense scenarios as well. So this is my intro into regular computing. So how does the quantum come into this? So for me to introduce quantum into this concept of computing, let me just take a sidestep for a second and tell you one thing about quantum that is important here. And that is a very weird property of quantum systems, quantum particles, or pretty much anything that's quantum. And that is something that is sometimes called the superposition principle. But in essence, what it means is that a quantum system can be in two states or even in two places at the same time. A very classic demonstration of this is this experiment that is shown on the slide here, where basically you have a wall with two slits in it, two holes in it. And there's another wall behind it where you can look at what goes through. And you can imagine that you do an experiment where you shoot balls at this, just, you know, whatever you like, golf balls or soccer balls or tennis balls, whatever you like. You shoot them at this barrier here. And you can imagine what would happen if you do this experiment at home, right? You'd have, I don't know how good of a shot you are, but you know, some of these balls will just fall down, will not be able to go through. Some of them will go through this the right slit and hit the wall behind it, and some of the other balls will go through the left slit and hit the wall behind that. So you'll get two lines of balls hitting the screen or this wall in the back, and that's the image that you're going to see. This is the classic picture of this experiment, or what would happen when you do this with regular balls, regular particles, whatever you want. However, if your particle, if your ball was quantum, then essentially what it means that it would behave in some sense like a wave. And what that means is that if I would shoot these quantum balls at the same barrier, then each one of these balls, each one separately, will go through both holes, both slits at the same time. It will be in both of these places at the same time. And then it will propagate further to the wall behind it and will hit it somewhere. And where it's going to hit depends on the details of how it passes through both of these holes at the same time. And the picture that we're going to get is very different than the picture that we get with classical regular soccer balls or tennis balls. So we're going to see lines of in places where these balls could hit, and they could actually hit right behind the barrier where there's no hole. So the fact that they can pass through both of these slits at the same time, the fact that they can be in both of these places at the same time means that they can then result in a very different picture, in a very different physical behavior. And that, in some sense, that hides the essence of a quantum system as opposed to a regular classical system. And I understand that, of course, this sounds kind of weird and almost unrealistic, and it's a kind of a long-standing problem in terms of adjusting our intuition to this type of behavior. And if you feel that this seems unbelievable, then you're in good company, because Richard Feynman, one of the top scientists and the top physicists of the 20th century, who got the Nobel Prize also, he said that if you think that you understand this two-slit experiment, then you don't really understand quantum physics. So if this seems weird to you, that's okay, but it does happen. And this has been measured experimentally many, many times with many different systems and in many different contexts, and has been verified experimentally to an extremely good degree. So the take-home message from this slide is that a quantum system, a quantum particle, a quantum ball, or any quantum system could be in two different states or even two different places, these two slits, at the same time. As opposed to, of course, classical systems that we know we cannot, unfortunately, be in two places at the same time, although we would have wanted to, probably. Some of you might have heard of a similar demonstration or presentation of this idea due to this guy, Schrödinger, who is one of the fathers of quantum physics. And it's this idea that's called the Schrödinger's cat. And he had this idea, no cats were harmed during this thought experiment, but he had this idea of having a cat inside a box that's closed off. And this cat could be subject to some vial of poison or not, depending on a particle that's been emitted here. So if the box is closed and we don't look at it, then this particle could be not in two different places at the same time, but could be at two different states at the same time. It could be both alive and dead because of this poison at the same time. So of course, this is not an experiment that anyone has done, but at least conceptually, this gives you another picture of this quantum property of a system being able to exist in two different states or two different positions at the same time. So now that we have this concept, we might not fully understand it, but we have this concept of the capability of a quantum system. Then let's impose it onto the computing infrastructure, the basic units of information that we were describing before in terms of regular computing. And the idea is that instead of a unit of information that's called the bit that I introduced before, this 0 or 1, we can have a quantum bit, which we call for short qubit. And such a quantum bit doesn't have to choose whether it's 0 or 1. It can be both 0 and 1 at the same time. It could be in both of these states at the same time, okay? And this little picture here showing a computer, a regular classical computer, saying 1, 0, 1. So it can say something, it can say some piece of information by presenting a string of bits of zeros and ones. A quantum computer at the same time, can say many different things. It can give out all the different combinations of 0 and 1 because each one of its quantum bits, each one of its qubits is both 0 and 1 at the same time. And in this little demonstration, we hide the crux of the speed up that quantum computing versus regular computing can give us. So we can basically use these quantum bits, quantum units of information to store all the different possibilities, to store a lot of information in them at the same time, and also perform all the different computations that we want to perform on all of these options at the same time. So we basically sort of maximally parallelize what we can do by using quantum properties for computing. And this is what we, at least in essence, mean when we think about quantum computing or using quantum properties for computing and how that could help us. So you can get at least a picture of how using these quantum properties could give us faster computers. Okay, and as I'll explain in a bit, in our research, we want to find a way how to realize such qubits, how to really make them happen in reality in the lab using Diamond. And I'll explain that in a second. But let me just very quickly tell you that if you remember this code, this RSA, that we're all using all the time when we shop online or access our bank's website or whatever, this guy here, Peter Shor from MIT, he's a mathematician and computer scientist. He wrote an algorithm, he showed that if he had a quantum computer, we don't have a quantum computer yet, but if we did, then we could easily break RSA. So if we had a good enough quantum computer that can check all the options very, very quickly because it uses qubits instead of regular bits, then we can very quickly break this RSA code that is ubiquitously used. So it would be a big deal, right? And this kind of brings us back or connects us back to the early days of regular computing, where this ideas of Alan Turing and the Bomba machine that he built allowed them to break a code that was previously essentially unbreakable. If we had quantum computers, they would again allow us to do pretty much the same thing. They would allow us to break codes that are these days essentially unbreakable. Okay, and that, you can imagine, that brings in some interest into the field of quantum computing. Everybody wants to be the first to have something like that, if that's at all possible. And even though this is an example of where the efficiency of quantum computers might shine, it's unclear to most of us. We have ideas, but it's unclear to most of us what we'd really be able to do with quantum computers in, I don't know, 20, 30, or 40 years. And maybe we'll have quantum Facebook. I don't know, but it's probably going to be a big revolution. And many companies are now, of course, many research groups in academia, but also many companies that you've probably heard at least of some of them, like Google and IBM and Microsoft, are investing a lot of money and putting in a lot of effort in trying to realize a useful quantum computer. They're making progress, slow progress, but still significant progress. And this recent result that Shmulik mentioned at the beginning, which is already about a couple of months old, is a first demonstration. This is from the Google group. It's a first demonstration of an actual quantum computer. So it's a small one. It only has about 50 qubits, as opposed to, I don't know, trillions that you have in your computer. But they've already demonstrated that it can do something much, much faster than the best computer, the best classical regular computer that we currently have. The only problem with, so this demonstration is quite impressive, and hopefully more advanced and impressive demonstrations are yet to come. So it's a real milestone, but keep in mind that this demonstration shows that we can do something with quantum computing much better than regular computing, but this demonstration is completely useless. So right now we can just demonstrate that it is better. We can't yet do anything useful with it, but it is better. And stay tuned, hopefully, to hear in the news about new useful things that we'll be able to do with such machines, hopefully not in the too distant future. So I hope I've given you a taste of why quantum physics and machines, computers that are built around these concepts of quantum physics could be useful and could be more efficient than anything classical that we currently have. And now I'd like to connect it to my own research and to an idea of how to realize differently than what Google is currently trying to do, to realize differently this unit of information, this qubit, and this time within Diamond. So Diamond, of course, I can imagine that all of you have sort of heard about diamonds, and maybe some of you have some nice diamonds. I have plenty of diamonds in my lab. None of them are nice like the one that's shown here. This is a picture from Wikipedia. We have different diamonds that are actually much better, but they look plain. And I just want to mention, diamonds are nice, but they're exactly the same in some sense. They're very similar to this piece of graphite. They're made out of carbon atoms. So diamond is an amazing material. It's just made out of carbon atoms, very similarly to this piece of graphite. But the spatial arrangement of the atoms, of these carbon atoms in diamond, is different than it is in graphite. It's a very special arrangement, and that gives diamond its special properties. And you can see this picture of diamond here and the picture of graphite are very different. Of course, diamond is transparent and graphite's not. Diamond is the strongest material that we know of, and graphite is kind of a very weak material. We can use it in pencils to write with. Diamonds are in a very interesting material with very interesting properties that are a result of the way these carbon atoms are arranged in space, okay, or kind of packed together within the material. But no material, no diamond, but any other material, no material is perfect. We never have a regular arrangement of a perfect ordered arrangement of atoms. And in this picture, I show you an arrangement of these blue balls are supposed to depict carbon atoms. This arrangement of carbon atoms gives you diamond. But there's never a perfect slab of diamond like any other material. There's always something in there that shouldn't be. And an example of that is that you could have this little ball that's marked with an N. You can have a nitrogen atom sitting there instead of one of the carbon atoms. And this happens a lot. In any piece of diamond, you're going to have this happening with some probability. So this type of defect, this type of impurity, where you have something that's not supposed to be there, so this specific impurity, this nitrogen atom, is very common in diamond, happens a lot. There's another type of impurity that could happen, and that is this little white circle with a V in it, and that basically is supposed to depict something that we call a vacancy or a hole. So it's a position in space where a carbon atom is supposed to be in, but there's nothing there. The carbon atom is just missing. So there's a vacancy at that spot. And this defect, this impurity that we call a vacancy, is also very common. It happens a lot. And the third impurity that I want to mention, the last one, there are many, there are hundreds of them that can happen. But the last one that I want to mention is both of these together. A nitrogen atom sitting somewhere within the diamond, and a vacancy right next to it. And that defect, because they're sitting right one next to the other, it has its own specific properties that I'll tell you about in a second. And it also has a name, and we physicists are not very good at coming up with creative names. So it's called a nitrogen vacancy impurity. And for short, we call it NV. And this is the defect that I work with. And why do I, and the community that I'm part of, why are we interested in this specific defect? Again, let me just mention, this defect is not rare at all. It happens a lot in many different diamonds. If by chance you have a diamond or have seen or heard of a diamond that has a color, it's kind of transparent, but has a kind of this reddish pinkish color, it's because it has many NVs in it. It has a lot of these defects. These defects fluoresce, emit red light. So it's not rare. And the diamonds that we have are diamonds that are synthetic. They're grown in lab, and we know how to engineer them to have this specific defect in specific concentrations that we want. So we know how to do this, and we know how to do this in a very controlled way using synthetic diamond. So synthetic diamond essentially is better than natural diamond that people dug out of the earth, because it's very well controlled, and in most cases much purer, much cleaner than natural diamond. And it's diamond for any other purpose or in any other measure. So why are we interested in this NV defect specifically? So we're interested in it because it has very nice, unique properties. One of these properties is the fact that it has something that we call a spin. So what is this spin property? I won't go into the details of it because it doesn't really matter so much, but you can just think of it as being a little magnet. It's like a little, actually, I like this picture. It's actually like a little compass needle. So it's this little arrow that points in different directions as a function of the magnetic field that it senses, okay? So this is a property of this defect that's called spin, and we want to use it. This spin property, again, is not that unique and not that rare. But what's nice about our NV is that its spin property, its little compass needle, is quantum. What do I mean by saying that this little that this little compass needle is quantum? I mean that, think about this compass needle pointing in some direction. So, you know, a regular compass would point in this direction or that direction or that direction, depending on the orientation of the magnetic field. And in the slide that you're seeing, I'm showing that it can point, for example, up or down. But our NV is a quantum compass needle in the sense that it doesn't have to choose. It can point both up and down at the same time. Going back to the examples that I mentioned before, with these particles being in two places at the same time, or Schrodinger's cat being both dead and alive, in our case, we have a tiny little compass within a piece of diamond that can be in two different states, pointing in two different directions at the same time. So basically, our little NV can be a qubit, can be a quantum bit. I'll call up 1 and I'll call down 0. And now I can store information, hold quantum information within this defect by having it point in two different directions at the same time and be essentially in 0 and 1 at the same time. And this is something that we've already demonstrated with our NVs in diamond. Actually, these defects are very nice because in addition to being quantum, they have this property even at room temperature. I don't have to do anything. I can hold this piece of diamond in my hand and it would have these NVs in it that would be quantum, that would be pointing in two different directions at the same time. So I could have this qubit just at room temperature without doing anything. And even more exciting than that, I can measure or read out the information in these NVs, in these qubits, just optically, just by shining light on my diamond. And these are very unique properties and are very, very useful when we want to try and take this system and make it into a device. So right now in my lab, we're working with support from the European Union. We're working on trying to take this one qubit, this NV, and actually taking, this is kind of an artist's conception of what we want to do. This is a kind of a sketch where we want to take a piece of diamond and have many different NVs, these little red balls here, each one of them a qubit. And then we want to connect between them with, to make them talk to each other, connect between them with these connectors. We want to make these connectors out of superconductors. And then we could potentially, hopefully, we're not there yet, but hopefully we can then build from that a quantum processor. We can actually make these qubits talk to each other and make some useful computation. So this is something that we're currently working on in my lab, but is still work in progress. We haven't been able to do that yet. Okay, so I think I've given you at least an idea of why quantum computers are good and how in my lab we're trying to work towards that in diamond, using a diamond as our substrate, as our material. But I think that you've also understood that this is, you know, still a little bit further away in the future. We're not there yet. We're working on it, but it's going to take some time. So let me just quickly, I don't know how much time we still have, but let me just quickly try to tell you about another type of quantum technology that we can, that we're trying to pursue using our NVs that is not related to computing. And it's related to the fact that these NVs, if you remember, are like little compass needles. They're sensitive to magnetic fields. So we can basically use our NVs to sense magnetic fields. So if you think about this arrow here as our NV pointing somewhere in space, we can shine light on it to make it point to a specific direction. We can control it using microwave fields, not a microwave oven, but something a little bit more complicated. And then as a function of some external magnetic field that we would want to sense, this compass needle starts to move. It starts to rotate. And then we can control it and measure it with light to get a signal that depends on this external field. So using a combination of light and microwave fields, we can measure very precisely magnetic fields using our little compass needle in diamond. And now the question is, why would we want to do that? Why would measuring magnetic fields with, you know, a small defect in a piece of diamond would be good for anyone? And an example of where this, so there are actually several answers to that. It could be good for a number of different things, but one example where this could be actually useful is magnetic measurements in medicine, in our body. And you probably all know of this device, this machine called an MRI. An MRI is an excellent piece of technology. It's really amazing. It's a very useful medical diagnostic, and hopefully you don't have to ever come across it. But it's a very commonly encountered tool that is really irreplaceable these days. And it basically, what it does is measure magnetic signals in our body. It measures little spins. We have spins in our body. That's what it measures. So an MRI essentially measures magnetic signals. That's what it does. But its sensitivity is limited. It's still amazing, but it's limited. And one example of where it's limited is that, you know, if we could have better sensitivity of measuring something in our body to be able to have an early diagnosis of, you know, some disease, some cancerous tumor or something like that, that would allow us to have a much more useful intervention at a stage where we can make a difference, where we can actually heal someone. So MRIs are amazing machines. They're based on magnetic sensing of signals from our body, of spins from our body. And even though it's really very, very useful, if it had more sensitivity, if it could see better, then it would be even more useful. It could allow us to do things that we currently can't do. And one idea that we have and we're trying to pursue is to measure magnetic signals, to measure MRI signals using our little spins in diamond, using our little NVs in diamond. And I mentioned to you earlier that we can measure everything from these NVs using light. We can just shine light on the diamond and measure these signals. So if we can do that, we can imagine a sensor where the little piece of diamond is attached to the end of an optical fiber. And now you have something that measures magnetic signals, measures MRI signals endoscopically at the end of a fiber. It could be handheld or it could be endoscopic, an endoscopic form factor. And actually what we can show is that if we can get this sensor head very close to the place that we want to measure, say endoscopically somewhere in our body or externally using a handheld device, it would be much more sensitive than the big MRI machines that we currently have, because we can get it very, very close, something that we cannot do with regular MRI systems. So this is the idea. We've actually demonstrated this in our lab. We haven't yet measured anything that's useful medically, but we've demonstrated that we can build this, this device with a little piece of diamond here at the end of an optical fiber. You can see the green light that we shine to measure the magnetic fields. And these plots here, I wouldn't go in, I don't want to go into the details, but these plots here actually show that we can measure magnetic signals with this tiny little sensor. So we're not at the point where we can use this to measure medically relevant MRI signals, but this is the first stage in taking this quantum system and trying to bring it over into an actually useful application of magnetic sensing. I'll quickly mention another application that is similar but a little bit different, and that is trying to address this sensitivity problem of regular MRI machines by using these NVs in diamond, but not to sense magnetic signals, but to enlarge or enhance the signal that the MRI system is supposed to measure. So, you know, we can't really do anything to our body. That's what it is. And the signal, the magnetic signal that the MRI machine is measuring is small. So, you know, its sensitivity is limited. But there's another modality of performing MRI measurements, and that is the situation where you can take some contrast agent, some chemical compound, some solution, and if that solution, you can enhance its magnetic signal, you can take all of its little spins, all of its little compass needles, and point them all in the same direction, its magnetic signal would be much, much larger. So if we can take this outside of the MRI machine, we can take this contrast agent, arrange all the spins to be pointing in one direction. This is something that's called hyperpolarization in the literature. And then you take this material and you inject it into the body, and your MRI system will measure that contrast agent as it goes through your body to specific places of interest. Then you would have a much larger signal than you usually would. And the interesting aspect here is that we can do this. We can take some contrast agent and polarize it, arrange the spins in it using our NVs in diamond, because we know how to arrange the spins of the NVs, and then we know how to transfer that polarization into a useful contrast agent. So that's the idea. This is actually something that we're pursuing as part of another European project, together with a large consortium of groups that include both academia and industry. And the idea is to actually build a demo machine that can hyperpolarize such a contrast agent for use in regular MRI machines, which might allow us to do things that currently we cannot do with MRI diagnostics, such as, for example, specific types of early diagnosis of heart diseases, of certain cancer diseases, and other things. So I tried to give you a little taste of how certain types of quantum technologies, MRI related here, might be actually not too far away from being able to do something useful for, you know, outside of you know, physics, or something that's kind of esoteric, but something that could be relevant to all of us. And hopefully that would work. I mean, this is these projects are funded on the scale of 3 to 5 years, so hopefully we'll be able to get something working out of that. So I'd like to finish up with this. I hope I kind of convinced you that the quantum revolution is here and now, is happening. I think that on the longer term, we might be able to see actual useful quantum computers coming out that would have potentially a huge impact on, you know, a very diverse range of topics, which we probably don't even know what they are yet. And maybe on the shorter term, we might be able to use quantum devices such as this little NV in diamond for other types of quantum technologies, such as this MRI type measurements. So with this, I'd like to thank you very much for your attention, and I'd be happy to answer any questions if there are.
All right, so again, if anyone has any questions, please submit them in the Q&A box. I think the first question, and this can be for both of you, is why does it seem like we're hearing so much now about quantum in the news, you know, in the last, let's say even the last few months, the last year?
Yeah, so if I can try to address that, then I would say that people in the academic community have been researching and working on various aspects of quantum science and quantum technology over the past several decades. So this has been an active field of research. I think that over the past few years, the progress has been such, and the achievements have been such, that they've passed some sort of barrier where it seems that they might actually be able to transfer into real world applications or to actual useful devices. And this is a transition that's just starting to happen, is just happening from more basic science into kind of real world engineering. And that is why we're starting to see actual companies jumping into the pool and starting to play around, like Google and IBM and Microsoft and others, more in the context of quantum computing, but not just. And also startups and other companies thinking about or appearing, trying to commercialize and actually industrialize to real world applications other types of quantum technologies, such as these companies that we're working with in this in these European projects and in other places. So I think it's what's happened recently is the fact that the progress has been such that it actually seems near at hand. And some examples are already out there. There are companies that are successfully building machines for quantum communications, which I haven't really discussed, and for other types of quantum sensors. So I think that this has propelled governments, industry, and academia to invest more money into this. This is then leaking out into the news, and hopefully will actually make real world impact in the near term future.
Great. Shmulik, do you have anything to add?
Just one comment that Amazon, the company I work for, is also starting to engage in quantum computing. I can't say more than that. There are a few statements that Amazon has made about that, but I agree with Nir that big companies are going to invest a lot of money and a lot of resources in collaboration with academia to make this revolution come as fast as we can. I do have a question for Nir, if we have time.
Sure.
Can you talk more about the, I'm going to put quantum on the side, but on the MRI, what would be potential benefits for the technology that you guys are kind of working on, this kind of small, high quality probe?
Right. So I've mentioned two potential approaches to improve MRI. One of them is this hyperpolarization idea, where we would be able to polarize some contrast agent that would then be injected into a patient going into a regular MRI machine. The other approach that you mentioned is to try to use such a local probe, this type of diamond at the end of a fiber, to be able to measure MRI signals very, very locally and with high sensitivity. So when would that be useful, or why would that be useful? I can give you a few examples, even though I'm not a doctor and I'm not qualified to really address the actual medical test cases. But I have spoken to several doctors, and for example, if you talk to if you think about skin doctors or skin diseases, then if you go to a clinic and the doctor would examine you, they would have no way of really knowing whether something on your skin that seems suspicious is actually cancerous or not. It's dangerous for you or not. And what they would do is they would either just assess it based on vision. They would just use their experience to decide whether it's suspicious or not. And then they would decide whether to take a biopsy and send it out for further examination, which could take a while. And of course, you can imagine that in everyday clinics, you cannot have an MRI machine that would be sitting there to really check this out. On the other hand, if you have this kind of little probe, and maybe I should mention this, even though there's a little piece of diamond at the end, it would still be orders of magnitude cheaper than a big MRI machine. It would be on the scale of thousands of dollars and not $1 million. So this is actually something that might be available in a clinic, in regular day clinics, and a doctor would be able to look at something that seems weird or suspicious and just measure it directly locally and give you information that otherwise would not be available. One can take this idea further into the endoscopic form factor. And these days, if a doctor wants to check what's going on inside, they would use an endoscope that basically has a camera in it. They just look, and they have no idea of really what's going on. And again, they can just decide whether they would like to take a biopsy in there or not. If they could have this real-time information on this specific region that they're looking at, that would be very useful. Maybe one last example of where this could be practically beneficial is scenarios where there's unfortunately breast cancer. This is an example that I've heard some statistics about. If you have breast cancer and unfortunately surgery is required to remove the tumor, the doctor would be inclined, of course, to remove as little as possible, but still to, of course, make sure that the entire cancerous region has been taken care of. And again, for the doctor doing this procedure, it's actually extremely hard to know where the border is or how much you need to really remove. And actually 40% of these procedures then require a follow-up procedure to make sure that to really take out all the diseased cells. If you could use this type of local probe in real time while performing this procedure, that would give the doctors additional information that currently they do not have, and would allow them to make a more informed decision on where the boundaries of this procedure should lie, and hopefully reduce the need for follow-ups. So these are a few examples that I've heard of where this could really make a difference and are not addressable using current technology.
That's amazing.
Yeah.
So we have time, I think, for one more question. And the question is, what type of software programs are required for a quantum computer to run? Will quantum computers require new computer languages?
Well, that's a very interesting question. I don't think that I can really give a full answer because we really don't have actually working quantum computers yet. But I can tell you that there are a number of academic groups, but also quite a few companies that have sprung out rather recently that are aimed at working on the software side of quantum computers. And I don't know what it would end up being, when things actually work. But the idea currently is that we're going to use regular computers that will run some interface language or some interface program that will then translate into quantum algorithms. And these are things that we currently know how to write. So we know how to write quantum algorithms that would then be translated into actual controls of the quantum computer. And these top layers of software of the classical interface and then the quantum algorithm language are things that could be generalized no matter what the realization of the quantum computer is, whether it's Google's quantum computer or my diamond system or whatever. And it's kind of funny, but there's an Israeli company called Quantum Machines that actually builds these things. They have a machine that acts as an interface between the quantum system, the quantum computer, and the classical world. And you can program it with their own language. They have their own language. Actually, there are a number of different languages that are floating around for programming quantum computers. I'm not sure which one of them is going to win out or something else. But they have their own language that can program their interface machine, which can then talk to whichever quantum computer you have and program it to perform the quantum algorithm of choice. So these things are of current interest. People are working on these things, both in academia and in industry. They work, but none of it is yet at the level where we can actually do something useful with it. And we're not at the stage yet where we can know what it would end up being when it actually works. I would imagine that it would look, at least in a kind of an overview or a bird's eye view, it would look similar to what I've just described. I can imagine only.
Great. So I think that that is all the time that we have right now. I want to thank both of you and everyone for attending. It really sounds like there's a world of possibilities, and especially with your research, the idea that you could really make certain aspects of healthcare a lot more accessible as well, and help people around the world, which is really amazing. So thank you again. Thank you everyone again for joining us. And again, to learn how you can get more involved, please email us at alumni@afhu.org, and we look forward to seeing you online or in person soon. Thank you.
Thank you very much.